Hello, my name is Dylan Meyer, and this is my 2022 SURF presentation. My project is entitled PCB Design and Debugging in Support of Laser Comm, Time Transfer Missions, and Testing. So I attend the University of Alabama and will be graduating in May of 2023. I'm majoring in electrical engineering, and the program I'm under for SURF is the Herbert Wertheim College of Engineering program. I am working specifically in the Precision Space Systems Laboratory in the Mechanical and Aerospace Engineering department. My plan is to apply for a PhD in either aeronautical or electrical engineering, and my goal is to work on atomic clocks and their applications in both industry and infrastructure. So what have I been up to this summer? I've kind of had two projects. So one is focused on the Click APD board and debugging that, which I will explain later in detail, as well as a redesign of Flashy, which is a PSSL optical table test component. It's been a mixture of laboratory experimentation. As you can see, I'm there with my mentor with some laser goggles. I've used LT Spice and Altium Designer extensively during my summer as well. So first of all, for some background, what is CLIC? CLIC stands for CubeSat Laser Infrared Crosslink, and it is a NASA mission with the payloads supplied by MIT and UF in a partnership. The general goal of this satellite mission is to demonstrate full duplex laser communication, which will entail both communication of data as well as time transfer via laser pulses. As you can see on the right, this is a general mission outline where the two satellites are deployed. They will communicate via laser comm. They will communicate the results of the laser comm duplex communication to the ground station. They will also communicate via laser communication to an optical ground terminal, and then they will engage in end-of-life operations. You can find more information about the mission at this link, and I would highly encourage you to give that a read. It's very interesting. So this is the receiver chain for the satellite. It's first started by a laser pulse. So those are used to communicate data via modulation scheme. It's then received by this APD, which stands for Avalanche Photodiode Board, and then is amplified by programmable gain arrays to amplify the signal so it can be received by the FPGA board. On the FPGA, it is run through a bandpass filter, comparator, and then a time-to-digital converter, which allows us to demodulate the signal. So this is a picture of the APD board that I was testing on. For scale, the holes that you see are 1/4-inch screws, an inch apart. So this is a very small board and operates at high voltages, and its role is to detect photons from received laser pulse and convert into electrical signals that can then be processed. It utilizes, of course, the highly sensitive avalanche photodiode to detect these laser pulses, and it's the first section in the signal chain, which that means it sets the baseline of the performance for the rest of the signal processing. So we were having some problems with the APD board. As you can see on this graph, we have noise present over the frequency spectra. There are several theories what was causing this. These spikes were only present with the PGAs had high gain, so we believe this was related to components, as well as boost converter noise and a possible gain anomaly that existed in the chain. So we also have another wrinkle in the problem where bandwidth of the response to the APD has to be fairly large so we can run several mission programs that would allow the satellite to operate successfully. So that creates problems with both negating noise at fairly low frequencies and preserving fairly high frequency bandwidth. So what occurred was filters were altered to allow for larger bandwidth for increased communication abilities. Grounding issues were discovered in the board, and white wire fixes were investigated. We managed to improve the performance via those fixes, and we'll integrate that into the board. Power supply filtering was also increased to reduce the 1.2 megahertz oscillations, and then The hopeful goal of this is to allow an enhanced SNR or signal to noise ratio, which will increase communication capabilities and make it more likely that the mission will be a success. The second part of my summer was FLASHY redesign. FLASHY stands for Fast Laser Advanced Switching High Frequency Emitter, and it is the pulsed laser used in the PSSL optical test bench. This laser is used to verify designs and make sure that anything that operates off of laser pulses or processes these pulses is working in a satisfactory manner and sort of serves as a baseline for the test bench. We wanted to reconfigure the design to be more indicative of the payload, have more triggering options, and generally be more user configurable. So what I did was I adapted the next generation click payload to the test bench PCB by altering several schematics and several necessities, such as chip shortages and different use cases, resulted in a fair amount of redesign. But the hopeful goal of this is to increase efficiency and test in the test bed for the lab, as well as better simulating spacecraft laser communications for a more realistic data set. So some lessons and skills that I've learned: general knowledge about laser comm systems. I had very little experience working with these systems, and it was really great to learn more and figure out how these things worked, general concepts that were important, figures of merit to look out for. Another thing that I learned was Altium. I've never worked with the software before, and it was great to get to learn the ins and outs of that. Practical RC filtering techniques and applications. Of course, every EE learns theory for RCL filtering, but not that many actually get to apply it during their undergrad career, and that was a real treat. Board design concepts, similar to RCL filtering. General concepts are learned in college, but rarely applied at this level in undergrad. And then the ever evolving quest of increasing problem solving and questioning skills. So being able to practically investigate what is wrong with the system and then ask the right questions to figure out how to find an answer to the overall problem. And then just a general introduction to graduate school matters of import: when to apply, how to apply, what matters in the application, what matters while you're here. Lots of just different tidbits that will hopefully help me on my way. And I would like to give a thank you to the PSSL team, Dr. Conklin, Dr. Clark, Danny Coogan, and Tony Davia, especially Danny Coogan. She's been my mentor for day-to-day stuff and has been a huge help this summer, and I can't thank her enough for that. I would also like to thank the UF Provost and UF at large for enabling surf. My fellow surf and REU students, it's been an absolute pleasure getting to be around you guys, getting to know you, and then finally you for watching this video. I appreciate your time and hope you have a nice day.